Anand, I'd like to present my project titled Image Processing Techniques in Real-Time Rendering, Shader-Based Visual Storytelling in Video Games, batch number 9, developed under the guidance of Mr. E. Raghuvaran. The domain of this project is in image processing and game development. Starting with the introduction, slow profit oriented transformation of the games industry has left gamers around the world unsatisfied with the quality of products and services they receive. AAA games, that is the Hollywood of video games, used to be the pinnacle of game design, content, graphics, and visual fidelity. Games are meaningful, passionate products with enough substance for gamers to want to purchase and play them. However, the advent of accessible online multiplayer, existing boring IPs, and a disregard for optimization has resulted in subpar products that cost more, take up more storage, and require higher processing power to run. This project was started as an attempt to showcase the possibilities of modern rendering and development technologies to make games that run well, are optimized, and still do not compromise on visual fidelity and graphics. So, the problem statement: the games industry frequently suffers from unoriginal gameplay mechanics, visuals, and progression systems. Users are left frustrated with the following pain points. As covered in the introduction, these are high storage requirements, processing requirements, increased intervention of online requirements, account logins, advertisements, monetization, microtransactions, etc. And this frequently leads to games compromising on one of the aspects of gameplay quality, visual fidelity, or optimization. The doubts on game ownership and the rapid rise in piracy is another problem that gamers face around the world. The solution lies in the designs of multiple systems that work together efficiently and effectively for their specific purpose. This project handles gameplay logic with separate C++ classes and interfaces, like, for example, the damage system interface and the gameplay ability system. These classes handle the data for the player and enemies, their abilities and characteristics, and the components that can be added or removed from either. This is a modular structure so that if, for example, further down the development timeline, new enemy types or new mechanics have to be added, this can be done easily due to the modular structure without having to hard code everything from scratch again. The visual layer, however, is handled entirely in Unreal Engine, the engine of choice for 3D environments that require real-time rendering like a video game. Two features of Unreal Engine are incredibly valuable, which are Lumen and Nanite. Lumen is Unreal Engine's path tracing engine, which is highly optimized for tracing light sources. It does not require pre-baked light sources, meaning that you do not have to light the scene beforehand and have to hard code essentially the light data inside a scene. And it allows seamless real-time rendering with provisions for improving performance using variable draw distances, which essentially means that the light does not render in the scene unless the character or the person that is viewing the light is close enough to it. This saves a lot of VRAM and processing power. The next is Nanite, which is a feature that controls the level of detail of polygons rendered in a frame. Every 3D mesh is made up of a bunch of polygons. These polygons, to appear high quality, they have to be rendered with a large number of polygons. However, this is a huge waste of resources if the models are far away and don't have the resolution to see them in the detail that they are rendered at. And Nanite solves this by dynamically changing the number of polygons a model renders based on its distance from the camera. Coming to the literature review, the base paper is Design Characterization for Black and White Textures in Visualization. So the motivation about this paper was designers use black and white textures when color is constrained or to keep hue free from for other mappings. Understanding how texture design affects perception and aesthetics is essential for good visual encoding. The researchers wanted to think of a way and try to identify how participants in the survey can recognize meaning and identity from a texture when the main components of what conveys the meaning is constrained, like, for example, the color. How did they do this? 30 visualization experts created designs which were 66 textured charts or maps, which was rated on aesthetics by 150 participants. The rating was a perceptual assessment on legibility and effectiveness. They found that black and white textures can be as effective as color or non-textured encodings for categorical data. Aesthetic preferences vary. Geometric versus iconic textures show trade-offs across chart types. How this is relevant to games is that textures and by extension procedural shaders, which is how the project conveys meaning through non-photorealistic rendering, are usable both to convey category or semantic information and to achieve stylistic narrative effects without relying on color or, in this case, realism alone. So, extrapolating that to this project, the paper takes advantage of suboptimal situations where color and detail is constrained, leading to designs relying on their structure alone to convey meaning and aesthetic appeal. In this game, we purposefully take away realistic rendering practices in order to convey meaning through the shaders incorporated per level. This method of non-photorealistic rendering advances the base paper's findings of being able to convey meaning and semantic information without relying on standards such as color and realism. The next is No More Shading Languages, Compiling C++ to Vulkan Shaders. It's a recent paper exploring modern shader pipelines with the goal of simplifying them. Shaders are layers of code that are an integral part of the rendering pipeline and affect the arrangement of pixels on screen. Shaders are written usually in high-level shader language, HLSL, or OpenGL shader language, GLSL, or directly in this project as material manipulations in 3D engines. Implementing different shaders on every level takes advantage of the modern methods of efficient shader programming as revealed by this paper. The next two papers are Interactive Technical Illustration and Recursive Gaussian Derivative Filters. These two are some of the foundations of the shaders implemented in this game. By following the second paper, the paper's conclusions, this game implements shaders of non-photorealistic nature as a storytelling tool. The third paper presents the mathematical basis behind the Gaussian filter. The Gaussian filter is one of the shaders is the basis of one of the shaders implemented in this game. The next paper is titled Stylized Rendering Techniques for Scalable Real-Time 3D Animation. This game implements shaders based on cell shading as an image processing technique as found in this research paper. Coming to the issues and challenges faced during the development period, firstly, the high VRAM requirement for in-editor performance in Unreal Engine. The development and testing system has only 4 gigabytes of VRAM, which is below the minimum recommended amount for Unreal Engine. However, the optimization practices used in the development period allowed us to create an environment and a game which ran even on a low VRAM hardware. Second is the procurement of 3D assets for characters and world building, static meshes, skeletons, animations, etc. We had to rely on pre-made assets and 3D models to showcase gameplay. Lastly, the optimization of Unreal Engine on non-Windows machines leading to difficulty in testing on macOS or Linux. The game is purely Windows-based for now. These are the tools used, Unreal Engine 5 and C++ for handling majority of the gameplay logic and the visual elements. Next, Fab, Mixamo and Blender were used to source these 3D assets as said before. Figma and UE5 widgets were used for UI UX mockups and implementation. Expanding on the architecture diagram, firstly we have the gameplay module, which has 3 components: the damage system interface, gameplay ability system, and the enemy AI system. The DSI implemented in C++ and C++ classes, it is basically a class structure that dictates what the character can or cannot do and how it is affected by other characters in the game with respect to combat and damage, which is the core gameplay loop. It has events such as on damage taken, on heal, on death, etc. These events are modified and configured in UE5 blueprints as necessary based on the characters. So for example, you could have an enemy type that is stronger than another, which could have a higher health and a higher damage output. Next is GAS, which is gameplay ability system, which is also implemented in C++. It is used to grant and deny abilities such as dash and dodges to the player. So for example, if the player enters a scenario in the game where the dodging is forbidden, we can use GAS to easily ungrant the dodge ability. Next, the enemy AI system. We use behavior trees to detect enemy that dictates enemy behavior, enabling enemy pawns to detect the player through AI sight, target the player, and perform attacks. Coming to the visual module, again 2 components: rendering engine, using Unreal Engine's post-process volume to implement shaders in each level. Shaders are programmed as post-process materials and applied to the scene as necessary. Next, the shader module, programming shaders based on image processing techniques such as Gaussian, edge detection, pixelation, etc. The following shaders are implemented: a cell shader, tool shader, dithering, and a Gaussian difference. Narrative integration module. The usage of shaders are a storytelling tool. The game story and narrative aspects are used to explain the visual identity of the world. The visual identity is expressed using the different shaders in each level. The module is implemented using character dialogue, UI prompts, and combat effects to showcase the world story. Now, with regards to the VRAM requirement of Unreal Engine and screen recording a live rendered game, we used a couple of screenshots to showcase the demo of the game. If you look at the first photo of the first screenshot shows the UI elements of a health bar and a combat timer, along with a pixelated shader and a creatively designed left to right scrolling 3D level with combat with enemies and progressive gates to unlock progression. Next, we come to the second level of the game, which showcases progress blockers like the glass in the background, which open only if the enemies in the particular section are cleared. We can also see the use of the cell shader in this and how it manipulates the lighting and textures of the player, the environment, etc. These are the references used for this particular project. And I'd like to conclude with that. Thank you.